Thank you very much. Good afternoon to everybody. This is the third of three lessons, three seminars concerning energy carriers, new powertrains, and in this last I focalize on the urban context. So I rely on what I said before. I will recall some slides that I already used, but I will add new ones which are the focus of today. Then after the summer period, I will start another kind of subject that is that of metros, of urban cableways and so on. But with this last, we finalize our goal of understanding which powertrains can be compliant for low emission private mobility in the urban context. So this is the goal of today. And in particular, I will address this goal with four sub-subjects. What do we intend for low emission areas, and are they to some extent defined by the law or not? Then which can be the compliant powertrains? I will recall the powertrains that I already explained in a previous seminar. And then this is the main point of today, which is the overall efficiency. Because if we look at CO2, if we look at the emissions, and considering what I already said, if we look at the well-to-wheel and the life cycle, then we need to know the efficiencies. So I will concentrate on this. And the last point is, can we split the driving cycle? Do you remember that I mentioned the WLTP, that is the worldwide harmonized driving cycle for calculating the local and global emissions? Can we be so, let's say, proud to propose a splitting of it? So far, it could be too idealistic, but we belong to university and we can propose ideals, or at least new solutions. So, as you remember, we already defined what is a sustainable system, a sustainable transport system, and the urban context, as you can see at the end of this slide, is that of urban context, because there we have 3 citizens out of 4 living in Europe in this context. So 3 people, sorry, out of 4 in Europe live in cities. So this means that there, in the cities, European citizens express mainly their daily mobility, especially for 4, 5, 6 days per week. Sometimes they go away during the weekend or they travel for work, but there they express their daily mobility. Sorry if I underline this normal, well-known thing, but it's important because when we will say which could be the compliant powertrains, this is relevant. And then, as you may remember, these are the variables that influence sustainability. Could be an interpretation, of course, but I will concentrate on 2 of them: energy and environment. Okay, let's start with this slide, which represents, on data published in February this year, the concentration of PM2.5. It's not the only element which contributes to local pollution. We have NOx, we have PM.10, but as you can understand, I took this one because in the area where I live, in the north of Italy, we have one of the most extended areas where the concentration of the particulate matter 2.5 is more extended, as you can see here. But there are also areas in Europe where there is a certain amount of concentration, and this is just one of the components of local pollution. But what I underline is that we are in Europe trying to solve as far as possible these concentrations. And this is related to the Directive 2881 of 2024 that I already mentioned in a previous seminar, and I will recall shortly. But the message that I'm providing you is that there are areas in Europe where the concentration of particulate matter or other local pollutants are more or less high. and we try to solve them. Then, as you may remember, more fixed installations in the urban context, I say today, mean less emissions in operations. Obvious, because typically we can rely on electrified line. So we differentiate at let's say the well-to-tank side the energy sources, and locally we typically use an electric motor, and this is positive because also we concentrate masses that have to be transported. So we are addressing trains, metros, automated people movers, and cableways. But I will not speak about them. They almost rely on electric traction and electric motors on board. We will concentrate on the distributed flows that are those related to private mobility. As far as we have a government presence, bids, tenders, and an integrated planning, we can rely more on fixed installations, less typically on private mobility. So more private vehicles means in general more emissions unless we address new engines, hybrid powertrains, electric vehicles, and we need to understand today which could be the most suitable ones. I recall again the passage from the Directive 50/2008 regarding the concentration of local pollutants, to which we associate this slide, the concentration, the period of reference, the permitted exceedances each year, okay? This is just a picture that becomes, as I mentioned before, and also in a previous seminar, becomes the Directive 2024 2881. And this implies, okay, again, I recall this slide, this requires some reduced limits to be satisfied, to be respected, in order to guarantee a normal use of the city. Otherwise, the public administration has to intervene. Okay, and it seems, it's said that from next year they could even receive a fee. Let's say have to pay a certain amount of money if they will not respect that. I'm not sure for that. It regards political aspects, but it's let's say it's said like that. You will also remember, you can remember that the passage. So I recall the elements concerning local pollutants. As regards global emissions, the CO2, the passage from 130 and nowadays 95 grams of CO2 per kilometer has been actuated in 2021, and European Parliament in 2023 has declared the aim to reduce these 95 grams of CO2 to zero in 2035. Notwithstanding this year, the European Parliament has said, well, we have to revise that, and I will try to provide some possible solutions in case. This regards also the light-duty vehicles. As you may remember, 175 was in 2015, and then it was reduced in 2021 to 147 grams of CO2 per kilometer. And this is the threshold of the fleet of each car maker. This is happening in other parts of the world, as I already said, so we are not alone as Europeans, but we are alone when we want to say that we want to reach zero in 2035. Zero where? Because the electric vehicles have no local emissions, but they have for producing the energy and storing the energy in the battery. And we need to find a solution. How? Okay, let's remember that we are referring to the WLTP, that is a conventional worldwide harmonized light-duty vehicle test that has been harmonized in the world, and we are referring to a conventional cycle. Nobody does that, but conventionally everybody has to respect it. Okay, and as you already know, we need to remember that if we deal with electric vehicles, we have not the tailpipe. So as I said before, we need to consider the energy chain. So these two graphs are a focus on something that I already anticipated in a previous seminar. On the top, you have the map, a generic map of an electric motor. On the bottom, you have a generic map of an internal combustion engine. If we look at the problem superficially, we would say, well, let's choose the first one, the electric one. We have from 82 to 94%. If we look at the bottom one, we say, well, we have from 10, 15 up to 30. This is on the vehicle. Nowadays, as we will see shortly, the internal combustion engine can reach 48% of efficiency. So no problem. I choose the electric one. Why should I choose the second one? The problem is, as I anticipated, the battery, because the battery has a low density with respect to alternative fuels that we have at disposal and needs time. And if we want to reduce this time, we need power. And if we want high power, we need to pay, and we need the electric grid suitable for providing that. Last but not least, we need to guarantee that on the territory. So since we need to arrive where there is the electric grid, if we rely on the electric power, we need to guarantee an electric grid. But on the other side, if we have a liquid fuel, we can bring the liquid fuel to the vehicle. So each of the two solutions have some positive elements and some negative ones. So in order to arrive to the best powertrains for urban mobility, we need to know the physics of the problem. And here we are. Now I start something brand new with respect to what I said in the last two lessons, and we analyze the well to will from the efficiency point of view. So let's suppose that we want an electric vehicle. I say, well, I don't contribute to local pollutants. So PM 2.5 that I mentioned before, PM 10, NOx, I'm not contributing. So I like that. But at the same time, let's remember that we want to contain the global emissions, so CO2. To do that, we need to look at the overall energy chain. And in this case, we rely, for example, on a thermoelectric power plant installation, which has a certain efficiency. The most, let's say, expected alternative is renewables, of course. But renewables means to have solar power, windmills, hydroelectric available for a great quantity of energy. Let's remember from my first seminar that transport systems absorb in Europe nearly 1/3 of the overall energy production. So if we want to provide alternative with renewables, it's a huge amount of energy that we want. And in a country like Italy, as I said also in presence in Darmstadt, we have 20% of the present energy production that is on renewables, and it has been obtained in 20-30 years. So we should add other 29%. So to say that we rely on renewables is just theoretical, and it will be theoretical for a number of years. Notwithstanding this, we try to address this goal. So let's start from the present situation. So going back to these numbers, we consider a natural gas and thermoelectric power plant efficiency. We are around 0.506, okay? With that, we can produce, and the natural gas equivalent efficiency 0.95, 0.97. And with this power plant, we produce electricity. This electricity typically arrives to the high voltage, which has to be converted into medium and low. This conversion is very efficient, typically 0.99, 0.95, 0.98, etc. But we have to consider them all because we have to pass from the power plant to the final use of this electricity. And typically we lose some points percent. I've read different sources in literature. We are around 6-7% in Europe. So from the power to the availability of this electricity. So the efficiency of the well-to-tank is something between 0.38 and 0.52. Okay? Then we want to use this power for recharging electric vehicles, but the CO2 emissions have already been, let's say, generated in this phase, especially in the power plant, of course. And then let's consider the time to wheel, and we are referring again to a battery electric vehicle. So we have a charger efficiency, so in the charging station, that can lose some points percent, minimum 3% is already too low, 3%, 4%, even 10, 12%. Then we have the round-trip battery efficiency, which depends on the battery itself. I cannot enter into too much details, but we lose 10-15%. Then if we have the aging effect, we can increase this loss of efficiency while charging the battery. Then we have the inverter efficiency on board, 0.95 more or less, and the efficiency of the electric motor that corresponds to the map that I mentioned before. It depends how does it work. 0.85, 0.90, 0.92, something like that. And then we have the transmission efficiency on board. We lose some points. I've not inserted, because it's very variable on the climate conditions, on the conditions on board that the driver wants to have, the BMS, that is the battery management thermal system, which implies, as we will see shortly, a certain variation in the overall efficiency. But anyway, resuming these aspects, I have the first part that is the well-to-tank, and we have seen before 0.30 something up to 0.5. And then we have the tank-to-wheel, where we have from 0.52 to 0.70. Okay? And what about thermal management? I quote literature, but we have similar examples in the electric buses experienced in Turin, the city where I live. In Turin, we have a part of the fleet of the public transport operator, which is a part of the fleet is electric. But since it's in operation with a certain number of buses from 2-3 years, we could, for the first time, analyze the actual energy consumption of these electric buses. But I didn't quote my sources because they have not been published yet, but these sources from literature. And the results, anyway, I can anticipate are very similar. So what you can see here is that the declared efficiency, that is something like 100 kilowatt hour per 100 kilometers, so 1 kilowatt hour per kilometer, and it's more or less the average value for these kind of vehicles. Well, this value already at temperatures of minus 10 or plus 20, 30 degrees is already 50% more, or even more than 50, the declared energy consumption. Why? Because at these temperatures, the battery do not work well, so they have to use part of their energy for obtaining a good range of temperatures for their operation. Plus, if you want to condition the vehicle, you need to use the energy from the battery. In the internal combustion engine, in winter time, if you want to heat the area where the passengers stay, well, use the heat from the engine, and it's, let's say, for free. Okay, so we didn't consider this in the overall efficiency because this varies, of course, according to the operational condition of the vehicle, of the road vehicle. Anyway, what the message is, we can have a variation of even of 50%, while on the internal combustion engines, this doesn't happen. So let's consider this data all together. And we have a variation from 38 to 52 in the well to tank, from 52 to 70% the tank to wheel, and the well to wheel makes something between 20 and 36%. So I think it's clear. If we look at the electric vehicle and at the electric motor, no doubt, the electric motor is winning. But if we look at CO2 and at the well-to-wheel, and just taking in as, let's say, input data, the efficiencies which provoke a certain combustion or loss of energy, then we understand that it's difficult for the electric vehicle to be winning in energy in any condition from the energy point of view, and without considering the thermal effect. An internal combustion engine has an efficiency, as we have seen, that is starting from 48%, but in the city it can be reduced below 20%. So in that case, the overall energy chain is in favor of the electric traction. While if the internal combustion engine can work well, that means not frequent acceleration and deceleration phases, not traffic jams, not research for parking, not traffic lights, then in that case, the overall energy chain is in favor of the internal combustion engine. You can have also that condition in the serial powertrains, hybrid powertrains, because the internal combustion engine is in operation in the highest part of the map. We will see that shortly. So once we have understand which is the overall efficiency, we can calculate for each case. I just gave you a very wide example, but you can calculate it for each condition. We need to consider which is the usage that the users of automobiles, of cars, make of their vehicles. And here you have a typical distribution from different sources. There is a comparison in the publication that I mentioned here, is an hyperbola. In this context, as I mentioned already in previous seminars, we have the left part of this picture, which brings us to say, well, where we have the lowest efficiency of the internal combustion engine, we have also the most frequent and short travels of a typical European citizen. While where we have the longer distances and where it is more difficult to provide the electric power, typically we have the highest efficiency of the internal combustion engine and longer travels which are less compliant with the autonomy of the electric batteries. Okay? So this means that we have to look also at the relationship between frequency and daily distance covered in order to couple that with the energy consumption of the vehicles and the idle time that we have at disposal. But the first main message that I want to leave today is that we can split urban context from extra-urban context. Where is the limit? Geofencing. So a city can decide that just the central part, historic part, is the one to be protected from environmental and traffic point of view, so the use of space, the use of air, or can decide that the overall surface of the city has to be protected. It's up to the administration, up to the condition. You remember that picture where we had the concentration of PM 2.5? Some cities could decide that the overall city has to be considered. So it depends on the local administration. But what I'm saying is that we can split local problems from extra local or extra urban problems. And the urban mobility can be, since it's frequent and with short distances, be more compliant with the need to have electric traction. So the decision of the European Parliament can be applied in an urban context, though from the, let's say, well-to-wheel and life cycle point of view, well, from the well-to-wheel, is not so compliant with an extra urban context. If we look at the life cycle, what is, let's say, separated is the production. A production of a vehicle in China, for example, where we have 63% of carbon, is something that has to be avoided from the point of view of CO2. From the point of view of the well-to-wheel, the electric traction in the city could be a good solution. But if we look at the overall picture, what I can tell you, and this is a second important message, is that it's not good to have this crash, this competition between the electric motor and the internal combustion engine. It's much better, and I say that in Darmstadt already, it's much better to have their collaboration. Let's recall which are the alternatives. So now I can point out which can be the most, let's say, relevant, suitable, and attractive ones. Micro mild hybrid are a good bridge towards full hybrid. They are, let's say, the entrance level. They already obtain something, and their, let's say, benefit is much higher, exactly where we need, that is in the cities. Acceleration phases, deceleration phases, and so on. But if we want to be serious, we have to look at full hybrid. And in the full hybrid, we have, I repeat, both the possibility to make the internal combustion engine to work at its highest efficiency, or to put it in parallel, this is in series, in parallel, electric motor and internal combustion engine. And this is the two alternatives, parallel or serial. Within this context, we can let it to have the plug-in, so to recharge the battery both from the internal combustion engine and directly from the grid. And this, again, in the urban context, is much more easier than anyway in the countryside, on the mountains, wherever you like, because you cannot have a grid that is, let's say, spread all over the territory. It would be something exaggerated to be, let's say, to be honest. The grid in the electric grid in the urban context is something that we can pursue. And then we have more for the future, the fuel cell, though they are already applied, but it depends on where we are looking at them. If we are looking at a professional use, like heavy-duty vehicles or, let's say, fleets, it's something. But if you look at the wide public, it's more difficult to provide the possibility to recharge or substitute the fuel cell in any context. Okay, given that, there is also the 48-volt hybridization, which is something that is much more promising in the last 2 years and for the next ones, as a sort of micro-mild hybrid that is more, let's say, similar, a bit more similar to a full hybrid. Is a promising alternative. So let's repeat this aspect in order to arrive later to, let's say, the resume and then the conclusions. The architecture of a serious hybrid electric vehicle implies that the internal combustion engines works independently from the use that is made of the wheels. That means that it works at the highest level. And this is already a great gain, because we don't work at 18, 20 of efficiency, percent of efficiency. We work at 30, 40, 45, 48 is the top of efficiency. And so it's difficult to win against that in the overall energy chain in a general context. It's easier, as I said, in specific context, but if it works by itself in that area of the map, it works well. And then you use the electric motor to vary the speed of the wheels with the mechanical transmission. And so you have the power that is stored in the battery, but the internal combustion engine produces that for the battery. And then through the inverter, it's provided to the electric motor. This is the same as before, but we have the motors that are on the wheels, motor wheels. So this is a perspective for the next future. It's already applied, of course. And you have a similar chain, but you have directly the motors on the wheels. Consider that the internal combustion engine have some new possibilities. I cannot reveal them already because they are under development, which allow it to work by itself at very, very high efficiency, even more than those that I mentioned before. This is a possibility for the future, provided that, differently from the vehicles that are nowadays available, this battery has sufficient power to guarantee the mobility in any city. Because the vehicle has to move, it arrives in a city where you have just a little zone that is protected, or in another one where you have all the city, so you need to guarantee some tens of kilometers. And typically nowadays, the full hybrid, not plug-in, do not guarantee that. They just guarantee few kilometers, except from a few models of cars. So in order to address the goal of moving by electric traction in the city, we need a battery of 10, 15, 20 kilowatt hour, which guarantees 50, 100 kilometers by electric traction. But still, you have an internal combustion engine for moving everywhere and anywhere. In the parallel, you have the possibility to have downsizing of the internal combustion engine because it's assisted, as I already told you, by the electric motor. And this allows to reduce a bit the mass, to reduce the consumption, of course, of the internal combustion engine, and to reduce the tank too. And this way you can guarantee battery, inverter, motor with a mechanical coupling the motion of the vehicle, but also through the internal combustion engine. The fact is that you should have a battery which actually assists with the electric motor, the internal combustion engine. Otherwise, the internal combustion engine will work more and part of the benefits of this hybridization will be lost. So it depends on the actual use that is made of this vehicle. You have to be a bit, let's say, educated to drive that vehicle. And then you have a serious parallel hybrid electric powertrain. I don't enter into many details, but it's a mixture of the previous two, and a plug-in hybrid. In the plug-in hybrid, already mentioned, but now we are looking at it with different, let's say, eyes, because in this context, it is very clear, I hope, that we can move in the city with the electric traction, with this battery of 10, 15, maximum 20 kilowatt hour, and without having a contribution to local pollutants. And at the same time, we have a very efficient distribution of power. And at the same time, we don't have to rely on the well-to-tank that I mentioned before when I referred to the electric traction, because we obtain directly the combustible on board, and there is not that chain that I mentioned before. So it's a good alternative. Let's remember that if we increase the dimension of the battery, we increase the mass, and this is not so good, especially in the deceleration phases. And the perspective for next year and even the next 4 or 5 years is to be at these levels. That is, anyway, as I already mentioned, 60, 90 times less than the energy density of an oil-derived fuel, which is something like 11.7 kilowatt hour per kilogram. So you can compare these two values and you understand easily that it's not convenient to bring energy in a battery. It's convenient if the battery has just to solve a problem, that is that of local pollutants. Otherwise, if it has to solve all the problems, the battery has to bring too much energy. And it's not competitive anymore. An increase of mass, an increase of time. If you want to contain the time, an increase of money. And if you have a damage of that vehicle, you have to change that battery. And it costs even more than the half of the cost of a vehicle. I would have some doubts of when I would be pushed to rely just on electric vehicles. Anyway, I've tried to underline the benefits of the electric traction, the limits of the battery, and the benefits of the internal combustion engine if it is used in a certain way. Sorry if I simplify a bit, but having the goal of containing the time, this is important. When I mentioned the typical use of the car before, I mentioned the idle time. Here you are, a distribution of idle time on a wide number of examples of vehicles from which we have collected data. And what is clear is that typically we have to recharge when we have time, not to be stressed by leaving a parking area, especially in the city where we have frequent changes in the use of parking areas. It's better to have a private parking. And not everybody has this at disposal, but let's suppose that somebody has, a certain percentage of people has, either in at home or where the person works, then it's much better to leave the time that it's available for recharging. And it's much better to have a low power because it costs less and it can be compliant with batteries that are not so big. We could say, well, I increase the power, so I don't have the problem of recharging them, but you increase the payment, and anyway, you increase in most of the batteries or some of the batteries, the aging effect for them. Given that, let's go back to the maps. So we have the internal combustion engine on the right side, the electric motor on the left side. Let's make them collaborate. This way, when the electric motor operates without using the internal combustion engine in the city, we have no local pollutants, it's clear, and it works well, much better than internal combustion engine because it's not so influenced by traffic lights, by traffic, by queues, and so on. But we do not have to rely too much, as I insisted enough, on batteries, just for moving where there is the problem of concentration of pollutants, so just in the city. It's better to leave the urban context to the electric traction and to leave the areas in any other place, on the mountains, at the seaside, in the countryside, outside the cities, in little towns, to the internal combustion engine. This is a map of latest research engines with an efficiency of 47%. So if you look back at the efficiency that I mentioned before, it's quite difficult or impossible to win against a kind of motor like that, an engine like that, with an electric motor, considering the whole energy chain. And look at the right side, of this picture, with the evolution of particulate mass limits, with the evolution of the class of engine from Euro 1 to Euro 7. Euro 7 is in force from July 2025, so from these months. So it's clear that we cannot say one solution is the solution for everything. It's much more serious to look at the overall picture, and the energy is not the overall picture. It's just the main element because of pollution and because of emissions. But if we concentrate on energy and emissions, again, we need to address a technological neutrality and keeping in mind the goal that I mentioned before, considering the numbers. So we have different possibilities for recharging, as we already saw last time with the grid, so plug-in, or wireless, or with the trolley, as we've seen in Darmstadt, with the lane from the airport of Frankfurt towards Darmstadt for the heavy-duty vehicles or the buses, possibly. And then what shall we do with this? Well, all of them could be good in this context, especially in the city. Outside the city, a bit exaggerated or too exaggerated, too impacting on the environment and on the electric grid. So this means that there is a number of possibilities if we concentrate on the city. Also, the battery swap could be a possibility, and there is a standard undergoing for motor vehicles or rickshaws, I mean the little vehicles, where the mass is compliant with the force of one person. Okay, and this is the battery swap. Given that, I have to arrive to the conclusions, so to leave some time for the discussion. I've finished earlier this time because it's the third and I want to leave more time, but today you are not so many, so maybe it's more difficult to have a discussion. Anyway, the main conclusion is that considering what we have seen today, it's much better to split the urban context from the extra-urban one. Even the WLTP, that is the conventional cycle, is much influenced by the urban phases, because those 95 grams of CO2 per kilometers that nowadays we have to satisfy are much influenced by the urban, let's say, motion, which increases the CO2 emissions. But what about splitting and saying, well, in this context, we don't want emissions at local level, looking at the life cycle, so we will avoid certain vehicles which come from abroad, from countries which have a high impact of carbon in the electricity production. And then we say, let's provide the, let's say, life cycle label. So the vehicle arrives in the city center and say, this is my life cycle label. If it's too high, it's not allowed. If it's below a certain threshold, which belongs to policies or politicians, well, we can say you are allowed it. But when you enter, you don't have to create a contribution to local pollutants. So this vehicle can continue by geofencing with the electric traction and having the possibility in a neutral approach to technology to get outside from the city with an internal combustion engine, where since we will use much less oil-derived fuels, we can use biofuels, e-fuels, so alternative fuels in a less, let's say, important way than today, so much more compliant with the possibility of using the ground for producing plants which will produce afterwards biofuels. So it's much more compliant as scenario. In this context, we can split urban mobility, and it will be up to the politicians, to the local administration to decide which part of the city has to be protected, and the usability of the internal combustion engine outside with this goal. Sorry, I have repeated some concepts, but I've arrived to the final steps of this sequence of 3 seminars. And the urban geofencing, consider that the Euro 7 in force from July this year already contains a sentence mentioning geofencing. So we have the door open if we want to address in that goal the double goal of local pollutants and global ones, global emissions. I've concluded. This is the conventional driving cycle. We would, let's say, remake it in the future, having much more sustainable cities. I hope so. Thank you very much. Thank you, Eva.